Okay, thanks for the nice introduction. I'm Martin Klissarov. I'm going to present you this paper called MaestroMotif and some of the related ideas behind this paper. I think they're quite relevant to the research that is being done at UCL thanks for having me. It's great to meet everybody here and perhaps make some new connections. So this paper is with a lot of collaborators from different places, from Facebook, from UT Austin, from University of Alberta, from Mila. So it's a big team. I just wanted to acknowledge all the people that are on the slide. So take a moment to look at these people later on. So the introduction was pretty nice, but let me just give a bit more context as to where I come from. So I'm just across the pond in Montreal, in Canada, and I did my PhD with Prof. Donna Prekop and Marlos Machado. And just recently, I started as a research scientist at Google DeepMind with Ed, which I'm sure that you guys know. And one of the cool things about Ed is that he always has these unusual hoodies and sweaters. So that's it's always nice to have as a supervisor. It's pretty chill. I'm kind of jealous of his sweaters, to be honest. I have to ask him about it. But okay. So some of the things that I worked mostly during my PhD is about temporal abstractions. So what is temporal abstractions? It's a fancy word, but essentially it just means skills or options. So essentially actions that last more than just one time step. And essentially we're surrounded with temporal abstractions all the time. So let's say that you plan your day. You're not going to think about it step by step. You're gonna have a high level plan about what you want to do today, what you want to accomplish, or where you want to go, and these kind of things. And this is something that we do, but this is also something that computers are built with, right? So here I have this representation of how we could see temporal abstractions in computers. And at the lowest level, we have that computers are using this machine language of bits, which is not very convenient to work with. I believe nobody has worked with that here, I hope. There's, if you go up the ladder, you see assembly language, which is also quite intense. I have never worked in assembly. And then after that, we have C++ and Python and all these things. And at the top of that pyramid, you have the graphic user interface, which is super convenient. And these abstractions, they essentially give us the ability to try a bunch of different things, to do research, to explore different ideas and get results fast, right? So one of the questions I had during my PhD is a difficult question, and it's about trying to figure out what is that latent space that we. In this case of computers, it's like we have built it, like we have already envisioned all of this. But how do you do that for reinforcement learning and for language model agents and things like that? Speaking of questions, if you have any questions at some point, just interrupt me. I'm happy to get your feedback and make this interactive. Okay, so let's start with a story to try to answer this question of what is a good latent space for temporal abstraction. So let's say that we're Bob, and Bob wants to become a versatile AI researcher, which all of us do. He asked his good friend Alice for advice. She's an accomplished researcher. She knows a lot of things that could be helpful. And she says, to become a versatile AI researcher, you have to practice the following skills. You have to create mathematical derivations. You have to write efficient code. You have to run experiments. You have to monitor the experiments. You have to write scientific papers, and you have to give talks. And all these things are super important, right? And one of the things that Alice believes is that once you master these skills, well, essentially, if you face a new project, you can essentially just recombine these skills and adapt them to what you're trying to achieve at that particular moment. So what happened in the story is, I mean, it's not a very long story, but essentially we're trying to answer the question of how to be a good researcher, right? And obviously what Alice uses first language, which allows us communication, and language is a great space for that, to communicate, natural language more precisely. But she could have used language to essentially try to give information about what code you should be writing exactly, what kind of keystrokes you should be pressing, and what words you should be saying to people, right? And you know, maybe they could have been like a whole data set, and we could have been fine-tuned on these experiences that the teacher wants us to have. But that's not what happened, right? That's not how information was communicated. Instead, what was communicated is a set of skills. That's what we saw previously, right? How to give talks and things like that. And the intuition here is that if we use language to communicate a set of skills, well, this is an incredibly efficient way to communicate a large amount of information. And that we do that pretty much all the time as humans, right? This is how we collaborate with each other. This is how we exchange information, right? What this talk is going to try to do is that we're going to try to take this approach that is very natural for humans and essentially adapt it for human AI collaboration. And we're going to do that with the hope of achieving zero-shot adaptation to complex tasks. So this is the preamble. Any questions so far? Make sense? Okay, cool. Right. So before we get into the details of what the method is going to be, let's have a little teaser to see what we're going to try to accomplish here. So let me see if I can start a video. Okay, so here's like a task description. Essentially, it says, so this is NetHack, just to put it into context. So NetHack is this, you probably heard about NetHack, I guess. People here work with Tim, maybe have heard about it. But NetHack is this complex open-ended game that that is one of the grand challenges as part of Balrog as well. So you might have heard it from Davide too and Bartek. Yeah, so essentially this is the task description that we give to the agent. We say don't leave the first dungeon level. There's multiple dungeon levels until you achieve XP level 4, which is like the amount of experience that you have gained in that level. And then you have to find a shopkeeper and you have to sell an item that you have collected. And after that, you have to survive for another 300 steps, right? So this is like the language description of what we want. And what the agent is going to do, forget the llama, it's going to ingest that and it's going to output a piece of code. We're going to go into the details of all of this in a minute, so don't worry about that. But essentially, it's just like a plan, essentially how you plan your day. So imagine that it is trying to plan how it is going to achieve this task, but with code instead, because language models are good with code, right? And essentially, what this piece of code is going to dictate is how a set of skills that have been, it's not important, the things that come up at the moment, how a set of skills, how this code policy is going to sequence a set of skills / agents to accomplish this task. And this is, once again, zero shot. And we see that these kind of tasks are kind of difficult, you know, they last multiple time steps. There's a 3D space, NetHack and whatnot. And this is another task, but it's not important. We're going to get back to the task. This is a bit of a teaser to essentially see how we're going to achieve that. Okay. Let me see, can I skip it? Okay, so the first part of this is essentially the same thing as what we had in our example previously, where we had Bob ask for guidance from Alice. And this guidance in this case is human intuition about a problem. We're going to understand something at a high level about what is important for a set of a distribution of tasks, right? So here it's represented a set of magic cards. So these are the set of skills that the agent has to master such that it can achieve good success on NetHack. And the way to obtain these cards or these skills is essentially with these three simple steps that we're going to go through. So the first step is going to be that we're going to craft skill rewards with AI feedback. I'm going to describe what AI feedback is exactly. The second step is that we're going to do abstract learning with in-context learning. And the third step is that we're going to learn these skills with reinforcement learning. Cool. All right. Any questions? So good? Okay. Okay, so first step, how do we get the skill rewards? So the way it works is pretty simple. It's a bit like LAIF and all these methods that we are using for language models. Essentially, we're going to have a set of problems that try to elicit preferences for each of the skills. We're going to do that AI feedback bit, and then we're going to have a set of skill-specific reward models. So what is AI feedback exactly? And particularly in this work, we use the method of MaestroMotif, which is that paper that we wrote before that serve as a milestone towards this MaestroMotif paper. So essentially what we get is that we have a data set of observations, and we present the language model with a pair of observations, and we ask which one is better for a particular task that we're trying to achieve. So concretely, it looks like this. That does the depth of the prompt. It's not very complicated. It just basically says what I just said now. Essentially, you have these two short gameplay descriptions, and here is what the preference, what is the preference that you should be seeking. And then here we have a skill description. So to give an idea, we have that, for example, the shopkeeper is going to prefer players that negotiate, sell, and interact with shopkeepers, but be careful not to steal from the stores. And same thing for a sender here. So essentially, like short descriptions of what we want from the agent, right? And at this point, the only thing that we want to extract is a data set of annotated pairs, where the annotations are essentially the labels of the language model saying this is good or this is bad for this particular skill, given the context that you have shown. And perhaps a couple differences with the previous work on Motif is that there's more information about the player statistics. We have a bigger model that we're using, and we have a larger diverse data set, and all of these things are super important. So just, more data and bigger models, that's the lesson here. Right, and what we get at the end of that is a set of skill-specific reward models. And we do that with the Bradley-Terry model, which is the standard method for preference-based learning. Any questions so far about this? Does it make sense? Yeah? Cool. Okay, cool. Okay, this is the second step now. So what we're going to give the language model at this point is a task specification, which is one of the things that we saw previously in the video, right? And a set of skill descriptions. And what the language model is going to output is code. So let's have a look at what the prompt is more precisely. So it essentially says that you're going to write code that defines the method select skill from the NetHack player class, right? And then it gives the description of the skills here. So the discover explores in depth the current dungeon and fights of enemies. And then the sender does this and that, and etc. So essentially, like high-level descriptions. So once again, it's communicating information at a high level in language to the agent. And the task specification is only saying what we're trying to achieve. So essentially, find a strategy that is going to let the player explore fully each of the first few dungeon levels, and then a bit more details about how this should be done. And the important bit here is that we're going to add this verification step, which is that your code is going to be verified through this unit test, and then the unit test is given. So what does that mean if we take a little step back? So what we have in the code portion of this algorithm is that first what we ask is that it outputs a high-level plan, essentially code that is gonna sequence the skills and is not gonna look into what are the low-level actions of these skills. Perhaps a skill activation is gonna be like 100 steps or 1,000 steps or something in that range. It just knows that it wants to activate this and tries to achieve whatever the skill is trying to achieve. And the second part is the unit test. So this is essentially a symbolic simulation of the environment. So it's written by the language model, and the language model is trying to simulate what would happen if a certain skill was activated in a certain situation. So we can think of this as the same thing as when we're trying to plan our day. We're saying, okay, I'm going to go to UCL, I'm going to give this talk, and then I'm going to go have dinner at this place, and you assume that everything works out, you don't assume that the bus is going to break down and then you need to take a taxi or something like that. So that's what I mean by optimistic, is that you basically assume that things are going to work out the way that you intended to work out. So yeah, these two things are generated by the language model, and the way that they connect to each other is essentially with the Python interpreter. So what happens is that you give this high-level plan, and you connect it to the unit test with the Python interpreter, and the interpreter, essentially what it gives you is an output, right? So the high-level plan executes with this unit test, and things are simulated. You get some kind of output from this unit test. It's essentially you're at this level, dungeon level, and then you activate the skill. You maybe collect something like this, some very high level kind of representation of the environment. So you give this output to the language model, and then you ask it, you repeat what the strategy was. Then you basically ask, is this correct? Does this seem correct to you? And then you ask it for some chain of thought. And as you say, use this to modify your code and generate. So you do some kind of loop of code refinement. We do that for about 3 times, not much more than that because it just doesn't work. And all of this is in context, right? Like the code is being changed and refreshed. And here's like an example code generation that we get. I'm not going to go into the details of that. It's just to say that it's kind of a bit complicated. It's not the simplest code. It has to pay attention to multiple things. Yeah, so it is able to deal with complex situations. Yeah.
Is the unit test just generated once? Was it generated on every cycle?
It's generated for every cycle. Yeah, you have like an original unit test, and then perhaps, let's say that the task is to collect some kind of item that you need to bring to a certain level or something like that. Then you have to kind of modify the unit test to represent whether that was achieved or not, or maybe you need to add symbolic representations of what kind of items you're collecting. Yeah. Yeah.
So I'm curious about, you mentioned that the refinement goes for about 3 cycles. How is that decision taken? Is that decided by the LLM, and essentially the output that says you get that output seems correct or not?
Yeah, exactly. That's essentially it. So it's this part. Does the output seem correct? Yes or no? If it says yes, then there's like a regular expression that collects that and then stops there. But we tried a little bit more iterations, but with the language models back then, that was just last year. They couldn't do. They get lost after 2 or 3 iterations. Yeah.
Question. So it doesn't have access to the game simulator. That's the
No. Yeah, that's right. Yeah. There's no source code that is being given here. It's all imagined, and we have to hope that the language model knows something about the game. If it's a game that is completely out of distribution, of course, it's not going to work. But luckily for NetHack, there is a lot of information on the internet, so they're trained on that too. Yeah.
How do you make sure that unit tests are actually in distribution to the states that the agent is going to encounter during the training?
Interesting. So how do I make sure it's in distribution? So what do you mean by?
Well, I mean, there could be certain situation that if you're going to be optimizing against a situation that the agent is not going to encounter because they are only occurring in certain levels that the agent is not going to get to. Will it actually transfer that well, or have you? Maybe you don't actually need to consider them.
So I think that the out of distribution aspect is definitely going to happen by interacting with the game, and some unusual things are going to happen. NetHack is known for that. You can ask Bartek about it. Yeah, it's I think like the unit test is just like an ideal representation of what might happen. And it's I would say that it's yeah, the language model knows enough about NetHack that like the simulation that it carries on is very sensible. Yeah, so once you execute in the actual game of NetHack, then a lot of things are going to happen, and it's not going to work according to plan. But it's still like a good start to have it going. Yeah. Cool. Yeah.
I think you once mentioned optimism in the
Yeah.
imagination process.
Yeah, which is cool.
And why was that necessary? Was there any particular behavior you've observed?
Well, to be honest, it was not on purpose. Originally, I didn't even think about it as optimism. But after talking with some people about it, they were like, yeah, it's like an optimistic take on what might happen in the environment. And I kind of like this perspective that, yeah, you're trying to plan for the best instead of planning for the worst. There is like, yeah, when I was trying to make the algorithm work, I didn't really pay attention to that. It was just something that came up naturally, but it would be interesting to see what are the trade-offs versus, you know, being pessimistic about what might happen in the environment. Yeah. Cool. Okay. Right. Okay, so step number 3. So at this point, what we have is we have that the human intuition has collaborated with the language model to obtain a high-level plan and a set of skill-specific reward models. And we still haven't interacted with NetHack so far, which is fine. But this is the third part where we do get to do that. So what is missing in this picture is actually a neural network that is going to interact with the environment. So we call it the skill neural network. The way that we obtain a skill neural network, well, okay, first of all, what is a skill neural network? It's essentially a neural network that will output actions that are going to be taken at each time step of the environment. So the lowest level of decision-making that you can consider. So this neural network is going to be trained from scratch on NetHack, and is going to essentially encompass all of the skills that we asked so far. So the 5 skills that we had. I think I never mentioned that there were 5 skills, but in this case, there are 5 skills. Right, so the way that we're going to get that is, yeah, the environment here is actually NetHack, right? And NetHack sends an observation or a state that goes to the skill neural network, but it also goes into the high-level plan, which is this symbolic piece of code that we had. And this high-level plan essentially is going to output the skill index. So it's like a one-hot vector that says, okay, in this state, you should execute this skill. And this one-hot vector is being essentially concatenated to all the other things that go into the neural network here, RGB observations and whatnot. And with this skill index, what we get is that, yeah, a certain behavior is going to be activated at a certain time. And when that behavior is activated, the other thing that is also activated is the skill-specific reward. So we have a set of 5 skill-specific rewards, and one of them is going to be activated and it's going to give some kind of feedback to the neural network as to what it did was good or bad. And as you can imagine, at the beginning of this process, nothing is going to be executed according to plan. Like the high-level plan is going to be like, yeah, I want you to activate the discoverer now, and but then the neural network is randomly initialized, so it's going to be a bunch of random actions. But as we repeat this process multiple times, as we encounter a bunch of states, and we kind of separate the states in which a certain skill has to be activated, versus another. And in those, let's say, subset of states, you get a specific reward for doing some things after multiple time steps, which is 4 billion time steps. You do get that the skill neural network starts to make sense. And then you can just basically, give it a skill index and it's going to act in a certain behavior, and you give it another skill index and it's going to be completely different behavior. So this is essentially reinforcement learning. And with this process, what we have is that we do get our skill neural network that is going to try to do the things at a low level that we are hoping with a high level plan. So the outcome of this whole training phase is that we have a high level plan that tells us how to sequence skills to achieve a certain task. And we also have a skill neural network that now is able to instantiate these skills in the real world or in NetHack. And this is cool because the only thing that we need to change at this point, if we want to achieve different tasks, we just need to change the high level plan with an asterisk that would say within a certain distribution of tasks that are achievable with a set of skills that we have defined initially. But we can come back to that. So essentially what happens at deployment time is that you now have a zero-shot adaptation where you give this task specification that can be quite complex, and you don't have to do additional gradient steps. Your skills are going to be acting in a way that you intended them to act. And the only thing that you really need to change is the high-level plan. And that's pretty easy to do because it's in context learning. So you just do like a few shot learning with a language model, and you pass it through a Python interpreter, and then you have a completely different agent in a sense, or high-level behavior. So this is the zero-shot adaptation phase. And NetHack, so just to give a bit of details as to what NetHack is in all of this, we have, NetHack is an insanely complex game that I think some people have famously said that once that we're going to have AGI before we have an agent that can solve NetHack. Just to tell you how hard it is, and this is from the people that have worked on the NetHack Learning Environment. You should try it out. It can be fun, I guess. So essentially what this represents is that each level of NetHack is, there's separate branches. The branch on the left is essentially the main branch, and it goes very, very deep, 50 levels deep. There's a separate branch on the right that starts off at some point, they call the gnomish mines, that goes into a separate direction. There's shopkeepers that try to sell you stuff, and you can interact with them, and you can try to sell your stuff too. And you have specific levels called Mine Town and Delphi and whatnot. So just to say that it's very complicated, and it's a great environment to try to make some progress with language models. Just like the Pokemon that we saw from Claude. I think eventually we're going to see NetHack, at least I hope so. So the kind of evaluations that we did here is the first set of evaluations that we try to reach some particular destination in NetHack. Some of the destinations that we try to reach is, the first one is called Gnomish Mines, the entrance of that separate branch. Then the Delphi is something that happens much deeper into the main branch, and Minetown is something that happens in the Gnomish Mine a little bit deeper. And we compare our method called MaestroMotif to a bunch of baselines. So the first one is the language model policy. So what the language model policy is, essentially you give it as context, everything that we give to MaestroMotif in terms of prompts, in terms of skill descriptions and all of that. And then you just ask it, can you achieve this, please? Can you achieve this task? But you have to act step by step. And I think it's not surprising that the results are really bad. As we see with Balrog, language models are really, really bad still at doing these kind of things. It's very agentic, right? And language models are getting there. So maybe you will have to revisit next year. But for now, this is definitely a result that stands, I would say. And so this is the category that we say zero shot. So you give it a new task and it has to adapt in context, and then it has to output the actions in the environment, and then we evaluate it and we see what is the success rate here. Then we compare to a set of baselines that are task-specific training. So essentially for each of the tasks, we gather preferences or some other method here called embedding similarity, and we try to train the agent to achieve these things from scratch. So for each of the tasks, we train the motif agent, for example, for a few billion time steps, and we see what is the performance. And we see that there's a big gap in performance once again between all of these methods and this MaestroMotif method. Then we thought, hey, let's try to look into tasks that are not just about reaching a destination, but something a bit more complex, maybe some kind of interaction with some entities in the game. Yeah, these are some of the tasks that we look into. Transactions, essentially, you go to a shopkeeper, you try to negotiate, sell, and buy, whatnot. The second one is price identification. So you try to sell something, but you don't really want to sell it. You just want to get a price so that you can identify whether it's a certain kind of item, because most of the items that you're collecting in NetHack are just, you don't know exactly what it is until you identify it. And the last one is BUC identification, which is blessed, uncursed, cursed. You're basically trying to see if you have a cursed dagger or something like that you have collected, and then you don't want to use it. So essentially, in this case, what we see is pretty much the same story. It's really hard for all of the methods to achieve this. With MaestroMotif, we make significant gains here. So yeah, this is about zero-shot adaptation to a bunch of tasks. Right, we also compare to a bunch of methods that instead try to maximize the score of the game. So in NetHack, when you do some things, you get some score. And one of the problems with the score in NetHack is that it's not a good representation of what you should be doing in the game. You can maximize score to millions of points, but then you don't really make that much progress in the game. It is correlated to a certain point. I don't have said it's completely uncorrelated, but it's not like it's not a great metric, at least for reinforcement learning agent. And what we see here is that across the same set of tasks that we just described, all of these baselines are significantly, we have significant challenges in achieving them. Right. So if we go back a little bit to one of the initial slides, we were trying to answer the question of how to be a good researcher, right? And we use language as a way to describe a set of skills. And I didn't say that at the beginning, but language is also a great space to give feedback. If somebody does something good or bad. I think it's probably the same thing that happens with your supervisors and my supervisors. That I would try something, yeah, that's cool, try more of that, or no, that's not a good idea, and then you let it go. But essentially, all of these things happen in the space of language, and that's great. But the other thing that's really important about language is that it's compositional. So if you want to describe a particular task, but then you want to add a bunch of constraints to it, and you want to add some particular way that you want to do something, it is possible to do it. And language is a great space to be looking into describing behavior. So we try to take that idea and we try to run with it. So we kind of had that teaser a little bit at the beginning, but what we did is that we took these 3 tasks that are quite complex. Maybe to give another example, we have here one of the tasks that is saying alternate between the first 3 levels of the Dungeon of Doom, at least once, until you collect a minimum of 20 gold pieces and defeat 25 monsters. Finally, try to quit NetHack. All of these things are very complicated and it's really hard to achieve them. And of course, what we see is that when we compare MaestroMotif to the baselines, there's a significant gap. The bad thing about these results is that all the baselines are at 0. So it's not great to have the baselines at 0. People might say we haven't tried hard enough, perhaps. So we did try a little bit harder. But yeah, this is just to give an indication of the average number of time steps required to achieve these tasks. So yeah, they're very difficult, like it's thousands of time steps. And language models, they can't do that yet. I'll get back to like this idea of long horizon and whatnot. But okay, so we tried a little bit harder, right? And what we did is that we had this human evaluation. So we essentially had these 6 paid participants, and they had no experience with NetHack before. And what we asked them is that we'd like you to practice NetHack for a minimum of 5 hours and attempt each of these tasks through 5 independent runs. And you don't have to spend 5 hours in a block. You can, play for an hour, and then you can look at the NetHack Wikipedia for another hour, or you can watch YouTube videos. You have essentially a lot of freedom in how you want to do it. So we compared essentially MaestroMotif to this human performance baseline, and that result is not in the paper, so I can only share it through talks, so I'm happy I can share it with you now. But essentially, we see that MaestroMotif in some cases is slightly below, but in most cases, it is pretty much the same performance as human performance on these tasks in this situation. And I'm not trying to claim that we have human level performance on NetHack, because there's some really cracked people on NetHack that can, really bring the level high. We don't have that with MaestroMotif yet. So clearly, there's a lot more work to be done here. So a bit of algorithm analysis here. What we have is that this code refinement procedure was really important to get good performance. So this is the normalized performance across all the tasks. And the important part in this code refinement is, that gives away what kind of language models we're using. We're using Llama 3 back then. We only got a good performance out of the code refinement strategy when we use the biggest model, which kind of makes sense. You need good capabilities to be able to reason across multiple iterations and whatnot. And another interesting thing that happens is we have some kind of emergent skill curriculum. And this kind of happen automatically. So going back to that slide where we had that reinforcement learning loop, and at the beginning it's completely random actions, and eventually it starts to make sense. Well, we have a representation here on the bottom right as to how this happens. So at first, what we have is that easier skills like the discoverer, which essentially means explore in pretty much every situation that you can and look around and try to, try to find things. This is the first skill that is being maximized. So this is the normalized skill reward. So how much it's maximizing, the reward that it's supposed to be maximizing. So this happens first. And after that, what we see is that other skills that are a little bit more complex, like the descender or the ascender, starts to get maximized. So these allow you to essentially, descend or ascend across levels and things like that. And then you have even more specialized skills like the merchant or the worshiper, which are essentially skills that only are activated at specific points in the game that you just cannot bump into by just randomly playing NetHack. So these are the skills that happen to be maximized last. So this just kind of nice curriculum that happens here. Cool. And I have this nice set of conclusions, but I'm going to skip that. I'd like to talk about this here. And open-endedness, I think, is something that you have heard about, especially in this lab. So open-endedness is this great idea that you have this never-ending stream of rich goals, right? It's complex. It lets you develop behaviors and whatnot. And on the opposite side, what we have is that hierarchical reinforcement learning, which is the method that we were using in this whole MaestroMotif algorithm, it's essentially breaking down goals into manageable sub-goals. So it's taking these large, complex goals, and it's making them approachable. And one of the spicy takes that I'm curious to get Tim's opinion on, one of the things that is said about open-endedness is that it is inevitable for AGI. Like we're going to have our agents be open-ended if we want to have AGI. But my take is that you also have to have hierarchical agents such that we can analogically achieve AGI. Right, and if you're a little bit more curious about this hierarchical reinforcement learning business, we have a whole paper about that. It's a bit of a survey paper that talks about all of the details surrounding that. And one of the things that is important to note is that hierarchical reinforcement learning, usually it is thought of as you have this, hierarchy of components, like you have different components that are kind of connected to each other, a little bit like agentic workflows or things like that. But what we try to argue in this paper is that hierarchical reinforcement learning is not restricted to the agent architecture, but it's all about exploration, credit assignment, and transferability, which are key to reinforcement learning and decision making. And that's it. Thank you.